So in this video, we're going to be going over the SI system of units. And the SI system of units is important to know because all of your hard science classes, including chemistry, are going to be using it. Basically, all it is an international system that everybody got together and agreed upon because they were tired of having one person writing with pounds, the other with ounces, the other with grams, etc. They're like, I'm tired of converting pounds to grams every time I need to use this equation. So how about we all just come together and agree we'll use the same units? And that's what they did. So when they were doing that, they realized that some units can be broken down into simpler units. So for example, maybe you'll have speed, so velocity. All that is a over distance traveled per unit time. So as you can see, the velocity can be broken into more simple units, a distance and a time component. So you don't need a unit in and of itself for velocity because you have simpler units that can describe it. So in their figuring out how to formulate the SI system, they came up with two classifications. They came up with the base units and the derived units. The base units were just the most fundamental units, and they were going to derive all of the other units from those base units. So for example, speed wouldn't be a base unit because distance and time can describe speed. So you don't need a whole unit for speed because you can describe it with simpler units. So what are the 7 base units? Let's start there. The 7 base units are the meter, the kilogram, the Kelvin, the mole, the ampere, the candela, and the second. And let's go over each of these in turn. The meter is simple. I'm sure everybody is familiar with the meter. It's just the measure of distance. So it is just measuring how far apart things are. Simple as that. The kilogram is mass. I'm sure everybody's also familiar with this, so I won't spend too much time on this. The Kelvin is the SI unit of temperature. So you might be familiar with Fahrenheit or with Celsius. Kelvin is the SI version of this. The reason that you use Kelvin instead of Fahrenheit or Celsius is that basically temperature tells you the average kinetic energy, so how much energy are in all the particles of the system you're looking at. And Celsius defines 0 as when water freezes. But frozen water, this little ice cube here, there's still kinetic energy in these particles. So this is kind of a silly classification of what 0 should be. So instead, what Kelvin decided to do was define it as when no molecule in your system is moving, when they're all at complete standstill and there's no vibration. That's 0, because that is literally as cold as you could possibly get. So that is all Kelvin is. It's just a measure of temperature where you can't go below 0, where 0 is the lowest, which makes a little bit more sense. What's the mole? The mole is super important for chemistry. You're going to be using this one all the time. All the mole is the amount of substance you're working with. So you might think of the mole as maybe 12 eggs is a dozen, right? So we could say a dozen equals 12 units because you could also have a dozen donuts, or you could have, I don't know, a dozen people. It's always going to be 12. In the same way, a mole is going to be an amount of something, an amount of discrete units. So How many? How many is it? It is 6 times 10 to the 23rd. That's what it is. So all you're saying when you're saying a mole is you're saying there are 6 times 10 to the 23rd of this thing. You could say you have a mole of people. That'd be quite a few people. That'd be 6 times 10 to the 23rd people. But usually you'll see a mole of a molecule. So if you have a mole of water, 1 mole of water, you have 6 times 10 to the 23rd molecules of water. That's what you're saying. 6 times 10 to the 23rd discrete units of that thing. So what's the ampere? This one's a little bit less important, especially for Gen Chem 1. It's important for Gen Chem 2, so maybe we'll leave a thorough explanation of this for later. But the amp is just the SI unit for current. All current is the movement of electrical charge. So you're going to have a wire, and there's going to be electrons moving through it. You can quantify those electrons moving using the ampere. And that's going to be important for the end of Gen Chem 2, where we're going to discuss electrochem. So maybe we'll define it better at that point. For now, just know it exists. Candela, this one is irrelevant. I would just know that it exists. It's a little bit antiquated, I believe. All it is the intensity of light. So its luminosity, how strong your light is. You don't have to really know anything about it. Finally, you have the second, which is the SI unit of time. Pretty simple. I'm sure you already know what that is. So now that we have the SI units down, let's talk about these prefixes. Many times, and right there in the SI units, you see kilo, kilogram. You're going to see the SI units in terms of one of these. Some of them you won't, like you never see like a gigakelvin, but many of them you will. You might see a microsecond, or you might see a millimeter. You'll see plenty of things like that. So let's discuss what exactly these are. So all these refer to is multiples of 10 away from the base. So the base units are going to be the gram, the meter, and the liter. Technically, you can just derive the liter from the meter. So these will be your main two, but the liter is handy and it's entrenched in basically everything. So we distinguish meter cubed from liter. We usually go for liter cubed. You're not really going to see any form of this except with maybe centimeter cubed. You're always almost going to see the liter. So all this is saying is that if you go up to deca, you're going to be multiplying by 10. Hecto, you're multiplying by 10 twice, 10 times 10, which is just 10 squared. Kilo, 10 to the third. Mega, you jump up to 10 to the sixth. And giga, you jump up to 10 to the ninth. And then if you're going down, you're dividing by 10. So for deci, you're dividing by 10, which is the same as multiplying by 10 to the negative first. Centi, you're dividing by 10 twice, which is just 10 to the negative 2. Milli, 10 to the negative 3. Micro, 10 to the negative 6th. And nano, 10 to the negative 9th. These are the big ones that you have to know. I would know these. Obviously, above giga, you'll have tera, etc. But you're really only going to run into these. It's also important to know the prefixes because you're not going to really show like gigameter. You would show GM. So what are all of them? Most of them make sense. So let's give myself a little bit of space here. There's really only one that doesn't make much sense, but you'll see why it's like that. If you are above the base, if you're multiplying by 10, you're going to be uppercase. If you're below, you'll be lowercase. So this is going to be D. Sorry, I messed up already. This will be D. This will be H. This will be K. This will be M. And this will be G, all uppercase. And then going down, you'll have lowercase d, C, M for milli. This one, since these are both M's, gets its own unit. It gets this little weird looking U, and then this is in. So these are all lowercase. And then pay special mind to this. Just remember, this is micro. This is milli. And then all you do if you want to write a unit in terms of a multiple of 10 is give it one of these prefixes. So for example, if you see 1 microsecond, it's the same thing as saying 10 to the negative sixth seconds, because micro is the corresponding prefix for 10 to the negative sixth. That's all that's saying. So that's just important to memorize. There's not much else you can do. I know there's mnemonics to help memorize them, so you could always use that. Like there's Great Mega King Henry died drinking chocolate milk, and then I guess just figure something out for these two because I don't know one for them. To round off the video, I thought that I would just go over some disclaimers and some of the more common units that you might have to be familiar with as you move through the course. And obviously, you're going to be presented with them overtly throughout the lectures. The first thing is mass. So the SI unit for mass is the kilogram, but we're using grams most of the time. For most things, you're going to be sticking with grams just because that is easier. But just know, especially if you're going to plug something into something that uses the SI system, more likely than not, if it's some constant, if it's some sort of equation, and it has mass as a part of it, it will be in terms of kilograms. But whatever you end up measuring in the lab, or whatever you're given as part of your practice problem, might be in grams because that's usually the one that we use in the lab. So just know that you're going to have to convert between them. So say you had 1 gram, you would have to know that that's going to be 10 to the negative third kilograms because there are 10 to the third grams in 1 kilogram. So that's the first important note. The next one has to do with volume, and it's a similar thing. So the SI unit for volume technically would be the meter cubed because the SI unit for length is meters and volume is length times width times height, or just length cubed. So it should be meters cubed, right? But nobody uses that. We always use liters, right? All the liter is 0.001 meters cubed. And why is it 0.001 meters cubed? Well, if meters cubed was easy to use, we would just use it. But the thing is, 1 meter by 1 meter by 1 meter of a vial or whatever would be huge. So it'd be a massive pain to have this in the lab. And it just turns out that it's a bit easier to scale it down by some factor. So we end up using the liter for that purpose. It's just 0.001 meters cubed. So sometimes you might have volume in a question that you're given, or you'll calculate volume in the lab, and you have to plug it into some sort of equation that takes volume into account and is in the SI system. Just know that you'll have to convert your liters to meters cubed. So those are the big conversion things. Now let's jump into a couple of the heavy hitters for derived units that you should know. Velocity is going to be a distance traveled meters per time seconds. And acceleration, which is similar, is going to be a change in velocity per time second. So that would just be meters per second per second. So meters per second squared. So these are two big ones to know. Velocity is a change in position over a change in time, and acceleration is going to be a change in velocity over a change in time. And then SI terms, it would be meters per second squared. Another important thing to know is going to be force. So in the SI system, we derive or we write force in newtons. And a newton is going to be force. Newton is going to be the term for force, and it's going to be mass times acceleration. Sorry about that. And why would force be mass times acceleration? Let's think about it. Force enacted on an object is going to be the object's mass times however much that force accelerated it. That's how you could find the force. Another way to think about it is if you apply a force to, let's say, a box here, and the box has some mass, the acceleration experienced by that box should be equal to the force that you push on it with, divided by however heavy that box is. So that's another way you can think about force. It's a force over some mass is going to be equal to acceleration. So what would the SI units for this be? Well, mass is in kilograms, and acceleration is in meters per second squared. So a Newton is a kilogram meter per second squared. And it's just the SI unit of a force. So the next important thing is pressure. This is another heavy hitter in Gen Chem 1. You're going to be using this a lot. So what is pressure? Pressure is going to be force over area, which in SI terms comes down to newtons per meter squared, or kilograms meter per second squared times meter squared. This meter goes away, this meter canceled. You're left with kilograms per meter second squared. Well, why does this make sense? Why would it be this? Well, if you think about it, if you're thinking about a pressure, what you're really thinking about is you have some container, let's say, and this is a horribly drawn container, but there's stuff inside this container, right? And it's pushing out on the wall. It's pushing out on it. Like if you think of a bomb, there's going to be stuff inside this, and it's going to be pushing out on the walls until the pressure's so big that it explodes. So that's what pressure is, and we all know that intuitively, that it's like the stuff pushing out on the walls of a container. It's the pressure. Well, if we want to quantify this, what we could do is just take one wall as an example, and all the stuff in here, and it's pushing on that wall, and it's bouncing off, pushing at it. We could just take the force that is pushing on that wall with, and take that over the area of the wall. So we get a force per unit area. What's the average force being pushed on this wall with? And that's all pressure is. It's going to be the force being pushed on this wall per unit area. Force per unit area. So, given our SI system, we know that force is the Newton, which is the kilogram meter per second squared. And the area is going to be written in meters squared because the SI unit for length is the meter. So now we'd get kilogram meter per meter squared seconds. And that's where we derive that the Pascal is a kilogram per meter second squared. Lastly, we have energy. The SI unit for energy is going to be the joule. And all that is a Newton meter, because energy is defined as the force being applied on some object over a distance. So if I push on this ball, or push on this box rather, with some force, and I move it a distance, the amount of energy that it took to move this box over here can be calculated by however much force I was pushing on it with, times however far I ended up being able to push it. And I guess that kind of makes sense, because if I pushed it farther, it would probably take me more energy. If I just pushed on it for a second and stopped, it probably wouldn't take me much energy, and it wouldn't move very far. So the energy is going to be the force times the distance. The SI unit for force is the Newton, which is the kilogram meter per second squared. And the SI unit for distance is the meter, so times meters. So this gives us that energy is going to be kilograms meter squared per second squared, and that equals 1 joule. We call those joules. So that's just a brief introduction to some of the units that you're going to be needing for chemistry. And as new units come up, we'll be discussing them thoroughly. This was just kind of an introduction.